So let's determine then the overall transmission coefficient, capital T. So here we're now going to form what are known as our Feynman sums. Capital T. So as you can see, we're going to get a whole series of these outward going waves, and by our notation, they should all be added together. So the first term we can see has this structure. It has a T plus, a P, and a T minus. And we can make a nice little mnemonic to help us remember this, because after all, I can draw a little picture of what happened to generate this particular term. Right? I can think about my two boundaries, and all that happened was my particle went through, he transmitted across the first upward step, he then propagated across the gap, and then transmitted across that downward step. So I got a final T minus. That represents the first term. The next term, this one, has somewhat of a longer history, but I think we can pick it out. And in particular, it really helps again to draw a little picture of what's happening for that term. To get this piece coming out, all that happened was I had come in, right? But then I had, instead of going through immediately, I had reflected back. And then when I, when I reflected back, I hit this other end and reflected back off of that one, like so. And I came across, and then finally I was transmitted outwards. So there's a whole series of factors that represent this, what's known as a particular history, right? There was the T plus where I transmitted inwards originally. There was the propagation P across, and the R minus because I'm hitting this downward step. I then propagate across P. I then reflect off of this step. Now this is what we had called the plus step, the upward step. But remember, when I'm traveling in the backward direction and hit it, right? To me, because I'm traveling backwards now, it looks like this downward step, so I actually use the minus coefficients. So that then is an R minus. There was the second propagation across, and then finally I transmitted T minus. So the final term then would be, if you tracked all those terms, T plus P, then there's R minus, P, R minus P, P, R minus, and then that R minus is followed by a P, and then a T minus. Okay, now let's look at the next term. It's going to get, really kind of nasty, but if we're careful, we can organize ourselves here very, very carefully. So what happens in this next one, as you can see, is I'm going to do just like I had here before, right? Because now this piece is going to go back for another trip. So I'm going to come in, I'm going to bounce back and forth, and then instead of going out now, I'm going to bounce back and forth yet again before I come out. I could go ahead, and label all of these terms. We're going to start to drive ourselves kind of crazy doing that. So let's think about the overall structure of these. Notice all of these diagrams have certain things in common. First of all, they all begin with an initial transmission and propagation. They all have this term at the beginning as I first enter into the new region, right? And they all also, notice, end with a final transmission out of the system, right? They all have this final transmission outward. So then what I think I can do, I want to organize my terms that way. So they all start with a T plus P. So let me put a little dot here to separate them. They all start with a T plus P and they end with a T minus. See, this one does as well. It has a T plus P and then it ends in a T minus, which I will separate out. And then this term that's in the middle evidently represents the rest of this process, which has this ricochet, right? It has this back and forth bounce that just happened with the R minus, the P, the R minus, and the P. In this term, right, I'm also going to have that ricochet, right, that has the, which is just, just another word for bouncing, right, because I've got the R minus, the P, the R minus, and the P. So that's my first ricochet event, right? And I'm all lined up either now to transmit out or undergo another ricochet, which is exactly what I do. And you'll notice these ricochet terms are exactly the same picture drawn over again. So I just get the same bouncing back and forth sequence as a factor twice. So I'm going to have t plus p times then this ricocheting process, reflect, propagate, reflect, propagate. And then it's going to do that yet again, reflect, propagate. So I may as well just square it, times then t minus, and then the sum continues. So what you see we have is literally just a simple geometric series. And we recall the formula for a geometric series. The final value is the first term, which you could always factor out, t plus p times a t minus. And then divided by then the infinite series, which always sums to 1 minus the repeated power, and that coefficient that gets repeated is this this ricochet factor, r minus p times r minus p. And in fact, right, and as you can see, this has to be correct because we've now effectively matched our boundary conditions. And in fact, if you take all the definitions for these little pieces, right, all those little factors that we defined in here, these fundamental events, this is sometimes called the Feynman rules because they tell you how to evaluate your diagrams, the Feynman rules, right, and insert them into this geometric sum result, you can actually prove that you get back exactly the capital T that we had solved for on a problem set using the traditional wave equation approach. So this really works. But notice, however, if we had left off any one of these terms, if we had ignored any of these possible sequences of events, any of these possible histories, we would not have gotten the right answer. So our claims then really do hold up, that our final result is indeed nothing other than the sum over all the histories, where the amplitude for each history is just the product of the events along that history. Very good. So at this point we will wrap up for today, and next time we will begin by considering actually the sequence of events that gives us the reflection, and then we will begin to think about cases where it's much harder to count up all of the diagrams.